So now that we've seen how to do calculations with lists using the .1 and .2 operations, now I'm going to show you a much better, a more visual way of doing calculations on lists. And this way is called pattern matching. And it's in fact supported by most symbolic programming languages. So the way it works is that we are given a list and we are given a pattern. So the list is a data structure existing in memory, but the pattern does not exist in memory. It's just a shape that we have to compare the list to. And this is done in an instruction called case. Oz it's called case. We have L as one of the arguments, so the actual list, and the other argument is the pattern. So what the case is going to do is going to compare the list in memory with the shape of the pattern. And the way the comparison is done is it's going to compare first the roots. If the roots are the same value, bar equal bar, the same subtrees, then the pattern matching can continue. So that's the case here. And then it goes on. And then what happens is it tries to match the H to whatever comes down on the left-hand side of the bar, and the T to whatever is on the right-hand side. So the H will reference 10, and the T will reference the rest of the list here. So this particular case is a case of successful pattern matching, and that means that the then part will be executed. If it would have not been successful, for example, the list would have been nil and not a list that was not empty, then it would have been doing the else. But in this case, it's doing the then and it's successful. Let me now show you a code example of pattern matching. For example, the sum function we defined before, sum L, instead of using L.1 and L.2, let's use a case statement. Case L of, and now we give the pattern, for example, H bar T. So this will match when L has the shape H bar T, and if it does, it will assign variables to H and T, and the result then will be the execution of the body, which will be H plus some T. And then the other pattern, in this case, for a list, the other possibility is that the list is empty, then it has to be 0. Okay, so this is an example of a list function written using pattern matching. So if I have now the list 5, 6, 7, and I run sum, it will give me the sum 18. Now notice that this function is not tail recursive. Of course, pattern matching works perfectly fine for making functions tail recursive. Let's make it tail recursive. So in order to be tail recursive, we have to add an accumulator, case L of H bar T then, and then what we do is sum 2, so the tail call, and then instead of L.2 we put T, and the result of the accumulator is H plus A, and the other case of nil, the result is A. So this is a tail recursive function written using pattern matching. So let me run this. Sum 2 of 5, 6, 7. We have to give the initial value of the accumulator. This also gives 18. Now let me show you an example of something which I call pattern engineering, where we can play around with the different patterns. Notice that these two patterns here, these two clauses, so a clause is a combination of the pattern and the code that's executed if the pattern is successful. These two clauses are independent. There's no overlap. There's no possible value of L that can make both of them true, which means that we can flip the order around. So let me copy and paste and do a small change here. Let me say, for example, now I have to be careful because in Oz, the first pattern is preceded by of, and the other is preceded by a symbol which is in fact two brackets facing each other. So case L of H1 bar, H2 bar T. This is a more complex pattern. This is a pattern which will match any list with at least 2 elements. And we have then sum 2, T, H1 plus H2 plus A. Notice that we have here a another case in the sum operation where we will extract two elements from the list and we will add them both into the accumulator at the same time. So this means that fewer recursive calls are needed. Let me call this function sum3, not to confuse with the previous one. So let me define this one. And if I execute it, browse of sum3, 5, 6, 7, 0. This also gives 18. So in fact, this is still correct. Notice these three patterns are not completely independent now. If I take the first two patterns, this one, H1, H2T, and HT, and I switch them around, then something undesirable happens. Then the second pattern will be masked by the first, and it will never be chosen. So pattern engineering is something you have to do carefully, and ideally all the patterns should be completely independent of each other, which means there should be no value of the list that causes more than one pattern to match successfully. And if that's the case, you can put the patterns in any order and the function will still be correct.